All right, most of these problems should seem pretty familiar from our notes on limits or problems that we've done earlier in the unit. So in question number 1, first we're going to find the slope of a secant. So we have to find out our y coordinates. So f of 1 would be equal to a y coordinate of 2, and f of 6 would be, let me try scrolling back there, sorry, f of 6 would give us the square root of 9. So we've now got our two ordered pairs, and the slope of the secant would be the change in y over the change in x. So we should come up with a slope of 1/5. If we had been asked for the equation of the secant, then of course you'd go one step beyond and do your point slope formula. So we really only needed the slope in this problem, I guess. Number 2, we drive 60 miles an hour, 60 miles at 60 miles an hour, so that would take us 1 hour. So 1 hour to travel 60 miles. And then we're going to travel 60 miles at 30 miles an hour, so that would take us 2 hours to travel the next 60 miles. So our elapsed distance is 120 miles, and we've managed to cover that in 3 hours. So our average velocity is our elapsed distance over our elapsed time. So our average velocity would be 40 miles per hour. Make sure, of course, that you label your units. All right, for limits, we've got all different kinds of strategies now. I hope when you look at number 3, you see a removable discontinuity, that there is a common factor of x minus 1. Our denominator is the difference of cubes. So you want to remember your algebra factoring method. So once we've removed the 0 over 0 problem, then we can do direct substitution. Let x be equal to 1, and we'll come up with a limit of 1/3. So there's a hole in the graph. When the x coordinate is 1, the y coordinate of the hole in the graph would be at 1/3, our removable discontinuity. And we can see that if we put 1 in for question 4, again we have our 0 over 0 situation, but we have factors here of 2x plus 3, x minus 1, and take out our common term of x. So our limit, our removable discontinuity problem, we factor the x minus 1, cancel, and then we can do direct substitution, put 1 into our variable. So we'll come up with 5 over 1, or 5. So another removable discontinuity problem. In number 5, same problem, but now we're asked to find the horizontal asymptote at the left side of the graph. So this is a left end behavior. Is there a horizontal asymptote? So let's remember that when we did our factoring a minute ago, same problem up above. Let me scroll back. Once we did our canceling, we came up with this value. The degrees are equal. We can see that from either version here. When the degree of the numerator is equal to the degree of the denominator, our horizontal asymptote would be at y equals 2. So that is also our limit. So our limit here would be 2. And in number 6, we've got a new function, and we're going to our limit at the right end of the graph. So again, a horizontal asymptote question for a rational function. This one also has some factors. We don't necessarily need to do the factors here for this problem, but we might for later problems. So let me just write this in its equivalent form. We'll use that in the next problem. But regardless, here we can see that we have a first power over a second power, first degree over second degree. Same thing is true once we've canceled a common fraction or factor, a 0 degree over a first degree. So our horizontal asymptote, when the denominator has a greater degree, would be at y equals 0. So that would become our limit at the right side of the graph. All right, let me keep that visible on our screen here. 7 and 8 are the same function. So notice our factored form here. So here we are talking about what happens at our vertical asymptote of -1. So in our factored form, let me try this again, from up above, once we've removed our common factor, then we can do our substitution here. And -1 is not the common factor. That's a vertical asymptote. So now we know our answer is next to the vertical asymptote. So x equals -1 is our vertical asymptote. So our limit close to the vertical asymptote is either positive or negative infinity. So let's check our signs here. So again, you don't need to rate this, but think of a number that's a little smaller than -1. So for example, -1.1, and you can see that the numerator will still be positive 87, but our denominator will be a very small negative number. So we know that this limit is going to go to negative infinity. So the numerator will be positive, but the denominator will be negative. Okay, so here we're doing our overall limit as x approaches -1. So the same problem, but we're at a vertical asymptote, so we know that the limit does not exist. There's an infinite discontinuity, so we cannot do a two-sided limit. We can only do a one-sided limit at a vertical asymptote. All right, question 9, we see our binomial term that has a square root. So our trick is to rationalize, whether it's in the denominator or the numerator, rationalize, and we will come up with x minus 9 for our numerator, and do not distribute in the denominator because of course we're expecting something to cancel. That's not a square root of 3 down there, just a 3. So we're expecting a common factor here because that was how the problem was written. And once we take care of our removable discontinuity, then we can use direct substitution and come up with our limit. So there's a hole in the graph, but our limit is the y-coordinate of the hole in the graph. All right, number 10 and 11 also have a square root, but not in binomial terms, so we can't do that rationalizing. But notice that we're looking at our end behavior. So here we're at the left end of the graph, and in 11 we're at the right end of the graph. So we're looking for horizontal asymptotes here. So there's more than one way to think about this, but notice that the square root, as x gets close to negative infinity, the -1 term is going to become negligible. And the square root of 4x squared is going to be the absolute value of 2x. So once we think of it this way, now we can see first degree terms, but the numerator is going to be positive, and we're going to negative infinity. So our numerator will be a positive 2 times something very large, very negative absolute value, so positive, and our denominator is going to be 4 times that value. So notice that we can think of our numerator as positive, our denominator negative, but the ratio of the coefficients is 2 to 4. So I'm not sure if I've made that very clear. Positive 2 something over negative 4 something, so we'll get -1/2. So it is the ratio of the leading coefficients except taking into account for the absolute value. So that's why we'd have a positive over a negative. All right, let's try that again with the limit going to positive infinity. We would still do our absolute value on the square root, but now as we let x go to positive infinity, the absolute value doesn't make much difference here. So in this case, we will have both positives, and our ratio will be 2 times a very large number compared to 4 times a very large number. So we will go to a ratio of positive 1/2. So negative 1/2 for number 10 and positive 1/2 for number 11. All right, number 12 looks like our theorem. If we could get this glob of 2x to match this glob of 2x. So our trick is to use our limit laws. We can bring that 3 out in front, and then we're almost to our theorem. So now we have sine of 2x over x, and we will have our theorem if we put a 2 down here, and the only way we can do that is if we also multiply our numerator by 2. So now we know that this limit is our theorem of 1, so we come up with 2/3 times 1. And our question number 13 looks like our other theorem, except we have a problem again that we would like this 3 theta and this 4 theta to match. So we use the same trick here. Let's bring the 4 out in front and then use our identity property. So our numerator we can't change, but we can put a 3 into the denominator as long as we put a 3 into the numerator. And we know this by our theorem is 0, so 3/4 times 0, of course, gives us a limit of 0. All right, in 14, what kind of trigonometry trick do I see? I hope you see that the numerator is factorable, and it looks like a quadratic with 3 terms, and I hope you're suspicious that perhaps it will have a common factor with the denominator. That denominator happens to have a GCF. And the numerator has a GCF, so you might take care of that first, or you might just go ahead and start factoring. But if we follow our factoring rules from algebra, you might do this first and then look for a factor of the quadratic. And I trust that it doesn't bother you that this is a cosine squared. Our factoring will still work the same as it would for other binomials. So 2 cosine x minus 1, aren't you suspicious that that's going to be your common factor from the numerator and the denominator? So that gives you a big hint. And then your other binomial factor. FOIL and check to see that you get back where you came from, and that looks good unless I have a sign error, and I think that checks out. So we can factor our common factors here, and then we've solved our removable discontinuity, our 0 over 0 problem. So then we can just do our direct substitution. That should have an x there. So the cosine of pi over 3 is 1/2. So we'll have 3/2 plus 2. So 3/2 plus 4/2, we should come up with 7/2. In 15, I think we want to simplify our complex fractions, so let's multiply the numerator and the denominator by the common denominator. And let's rewrite, so we're doing distributive property here. So in the first fraction, the 4's cancel, so we'll get an x, and in the second term, the x cancels, so we'll get a 4. And again, don't distribute, because I think you know you're expecting something to cancel here. So there goes our 0 over 0 problem once we cancel a common factor. And now we can do direct substitution. So we'll come up with 1 over 16. All right, in question 16, perhaps our limit laws might serve us well here. So the limit of a product can be the product of the limits, and we don't have any trouble doing that. So direct substitution works just fine here. So we'll have 7 and the sine of pi over 4. I like the 1 over square root of 2, the pre-rationalized form, because the sine and the cosine are the same, so these two have a product of 1/2. So there we come up with another answer of 7/2. And when we go to infinity, trick question, does a sine wave, this 7 can come out in front if you wish, but does the sine wave have a limit? So we know that the sine wave always stays between +1 and -1, but those are not horizontal asymptotes. You might say that those are maximum and minimum boundaries, but it constantly oscillates. So on the right-hand side, is there any horizontal asymptote? No, there is not. So the limit does not exist. All right, a couple true, false. U's are given here. We know these are questions about limit laws, I suspect. We are given the limit as x goes to a of f of x, and we're given the limit of g as x goes to a. Notice that that's a 0. All right, so our limit laws work as long as we can avoid division by 0, and as long as we can avoid square roots of negative numbers. So our limit law here in number 18, the question is the limit of this difference equal to the difference of the limit? So notice that we brought the 3 out in front, so we did the limit. Maybe I should say first we did the limit of each term separately, and then the constant came out in front. And there's no problem here with any square roots or division by 0, so that would be perfectly fine. As opposed to number 19, the limit of a quotient, is it the quotient of the limits? And that sometimes works, but here we have a division by 0 problem. So we cannot apply the limit laws here. There might be a limit, but we can't find it by the limit laws. And I think you might be suspicious in number 20 when you see the radical, but notice it's a cube root. So this, we know that the limit of a root is the root of the limit. So we could rewrite this way, and we could rewrite this side. So is the limit of a root the root of a limit, as long as you're not putting a negative under that cube root? And the limit of f of x is -8, so in fact we'd have no problem there coming up with a -2. So our limit laws hold for that problem. In 21, here we have a square root. Can we do the square root of the limit when we're talking about f of x? And here's our problem with putting a -8 under the square root. So sometimes it will work, but here it fails. All right. And here we want to pick the graph that satisfies these limits. So here we have limits as x goes to positive and negative. So here we have the end behavior on both the left and the right-hand side. So in other words, we need a graph that has a horizontal asymptote of 0. So the only 2 possibilities then are B and C. And now let's narrow it down. As x goes to -1 from the left side, we go up to infinity. So -1 from the small side, we need to go to positive infinity. So I think that rules this out. From the small side of -1, we go up, and from the right side of +1, we go up. So those two check out. And then I think just to be sure, we should check our last condition. If we're on the right side of -1 or the left side of +1, we should go down to infinity. So I think we're happy with letter C. All right, in 23, here we know that if x goes to infinity, the 2 and the -1 become negligible. Think about x becoming huge. So we could say that this is approximately equal, not exactly, but again, the square root of 4x squared, as long as you write absolute values there so that you check out the signs. And as x becomes huge, the ratio here would become 5:2 because both would be positive when we're going to positive infinity. And here we've got the same problem in 24, but notice that this time we're going to negative infinity. So our ratio is not exactly 5:2 because the numerator will still be positive, but as we go to negative infinity, our numerator will be negative. So here we get -5/2. -5/2. Okay, so there's an example of a function that has a different asymptote on the left end and the right end. All right, our limit laws again. So our limit of the sum of terms is the sum of the limits, and our limit of a root can be the root of the limit. And if we let x go to negative infinity, as we let x get smaller and smaller, the squared term is going to be so much bigger. So if we say that the squared term is much larger in size here, we could say, well, the battle of the terms here is going to look something like this. This square root is going to look like an absolute value. So as we go to negative infinity, these two terms are going to send us closer and closer to 0. All right, in 26, if x goes to negative infinity, I think we're going to see this better if we get a common denominator. So let's see what happens if we multiply the first fraction by x squared plus 1. Sorry. All right, let's try that again. I'm multiplying the first fraction top and bottom by x plus 1. So we'll come up with these two terms, and I'm going to multiply the second fraction by x minus 1. And just to be careful here, I'll keep the parentheses there for a second. And our denominator, of course, would be x squared minus 1, our common denominator. So we can see what happens here is that we will come up with a 6x squared over an x squared minus 1. So the degree of the numerator and the denominator are equal. So the ratio of our leading coefficient gives us our horizontal asymptote. And notice it doesn't matter that we're going to negative infinity because we're squaring those x's. All right, sorry, this is getting a little long, but we're getting close here. All right, what happens with the product of these two as x goes to infinity? We can say that the limit of a sum is the sum, or limit of a product rather, is the product of two limits. And then we can think what happens as x goes to infinity. This term is always ranging. It oscillates from -1 to +1. And this term becomes huge. So what happens as we take a very huge number and multiply it by a positive or negative fraction? Is it ever going to get closer and closer to any specific value? And I would say not. So I think So our limit does not exist here. What happens if we have this term, the limit of a quotient? Let's split this up into the quotient of two limits, as long as we don't have a 0 in the denominator, and of course we don't. Our denominator is going to get huge. Our numerator, of course, is always again going to be somewhere between -1 to +1, but we're dividing it by a huge number. So remember what happens as the denominator grows larger and larger. The value of our fraction is going to go to 0. All right, and now we want to do some one-sided limits here. On the small side of -2, so we're using this part of our piecewise defined function. So what happens if we choose a value a little bit smaller than -2? This x is going to get very close to -2, and it's going to become the square root of 4. So I think we should come up with, I better check my work. I think I copied this wrong here. I'm dropping this negative sign, is why that doesn't seem right to me. So let's try that again. A -2 plus a 2, so we're going to have a 0. And as we go to -2 from the right-hand side, then we're in the middle of our domain. So if we pick a number close to -2 and we put it in for x, that will give us the value -2. And finally, if we want our overall limit, the question there is, did the left-hand limit and the right-hand limit agree? So in A and B, if A and B did not agree, then the overall limit does not exist. All right, let's try again with the other value. What happens if we're on the left side of +2? The left side of +2 takes us to the middle section, so that would give us a +2. And on the right side of +2, we would be in this part of the domain, and we would put a 2 in by substitution. So we would come up with a 4 minus an 8 plus a 6. So it looks like here we would come up with a 2. So our left hand and our right hand limit agree, so we come up with an overall limit of 2. All right, I apologize, that was a little bit longer assignment, but hopefully it's helped you put together a lot of the different types of limit problems.